I'm so glad you just said that. That's really weird because, of course, I totally do want this to be recorded. Yes, for your sake. Yes, thank you for. And in the other class, for some reason, it wasn't recording, and someone asked that like halfway through, and I was mortified. So we started recording, and then I was going to make a big deal to them to tell them to watch the recording of your class just in case. And this class, I could have sworn I made a big point of making sure to press that button right before we start, but I guess I didn't. Anyway, yes, thank you. Sorry, my bad. Yes, we're totally recording from here on. Yes. And I will post it. And right, good point. Okay, so we're gonna start. I'm gonna start by going over right from the beginning. I'm not gonna go over every single. We're not going to go over every single detail of this whole practice exam, because that's why you have written solutions to it. But I am going to start right at the beginning to say some things that I've already realized that are already either confusing or something. And so, but I'm going to try to write on my screen. So please have your questions in front of you. I don't know why I'm making this so difficult. All right. So at the very beginning of the exam, here we go. At the very beginning of the exam, problem 1, part A. I want to talk about that, even if whether you think it's easy or hard. I want to talk about that for a second before we go any further, because it sets an exam tone, sort of. So, okay. Okay. Now stop me if I'm wrong, but I believe, like what I'm writing right now on the screen, I believe I'm writing, correctly what the given is. There's another part of the given as well, I know, but this is problem 1, part A. You're given this differential equation, which is meant to be somewhat familiar. Like hopefully when you look at it, you're like, yeah, that's not a shock that I would see something that would look like that. But you might also look at it and be like, what's going on in those parentheses? I'm not sure. I've seen a Q before in this class. I don't know what's going on with this capital R cube business. Like all that is fair. But then I ask you to do something with this, right? Before we go any further, or we think about questions or answers or anything, something I want to make very clear that I should write in the document itself, like I will in an update or I will in the real test. But what I want to make very clear, hold on, sorry, is that I'm incompetent. That's what I want to make clear. Oh my heavens. Okay, what I want to make very clear. Yes, I just said, oh my heavens. I don't think I've ever said that in my life. What I want to make very clear. Okay, one thing, when you're reading these problems in general, these type of problems, I really should say it, and I will try to put it in, again, I will try to put it in the actual text of the actual exam. I should have, but whether I say it or not, it is true. You should believe when you see a problem like this, presented like this, you should believe that X and T are variables. And the reason you know that is because the derivative is written in that way. Like you can't take the derivative of anything but a variable. So like the left side is signaling you that X and T are the variables, particularly that T is the independent variable and X is the dependent variable. And anything else you see there, I mean, I want to be super clear, even if you've never seen it before, because this could happen in the real exam, even if you've never seen a Q before in this class or an R, like put another way, even if you don't know what they refer to, like even if you understand enough to know that they're probably measurements of some kind, but you're like, of what kind? Like what? Doesn't matter. The first and foremost thing that you want to believe about them is that they are constant numbers, positive constant numbers just being unspecified, but that they are constants. You can and should assume that for a problem like this. Okay, that's point number one. Furthermore, yes, assume that t is an independent variable and x is a dependent variable. Wait, that was okay. That's the main thing to assume. Okay, now then, well, then as we solve this first problem, we're going to solve this very first one, because even if you got it right or you think it's easier or whatever, I have come to understand from the other class that actually I made a careless but sort of confusing error in my solution to this very first one in the solution I posted. So I'm going to solve it right now correctly and show you where the error is. I'll repost that also, but just before we even get any other, and I'm just nervous about it because I hate making errors, you know, like near exams, because it can like throw people off. So we're going to do right now part A, sub point 1. It is done in the solutions, but if you're tracking along, you'll see I made an error in the solution that I want to correct right now, and then everything else is fine so far as I know so far. But and I'll alert you when we get there. But here we go. So we're given this differential equation. We're also, and then we're asked, as we typically are in these kind of problems, we're asked question is, we're asked to consider this, and tell me if I'm wrong. I believe it was something like this. And again, please, like if you're following, please correct me if I've written this wrong, but good. This type of question here, so I'm just like rephrasing it again. This type of question, you know, of course you're getting, I almost hope you're getting sick of this question, getting bored of it, because that means you're seeing that we're doing it all the time and you're maybe starting to master it. We are all the time asking this question: does this x of t function fit this differential equation? Does this position, does this description of motion, does this description, where you plug in the time and I tell you the space, does that description match a differential equation that somehow we know to be true of the system? Like that's like always our question, right? And that's our question right here. Notice that this form of the question, part A, that I'm making a big deal of right now, it's like super similar to part B and C. Like it looks like you're just being asked the same exercise like 3 times to practice something, and you kind of are. But there's also a very subtle difference between A and B and C that I'm trying to address right here in A, which is that A, we actually haven't mentioned physics at all yet. This really is math. Like the reason I call the problem math, I know all of physics looks like math in a way, but this is really math, because I haven't even mentioned anything about oscillation or springs or like anything here, which makes it either easier or harder depending on who you are. But like there's no physics in this question. It's just like literally, does this one equation, is it consistent with this other equation? Okay. And the way to answer that always, and I know you guys know this, but the way to answer it is to take derivatives. Like we're going to find, to know whether, if we're being asked whether this is a solution to this. Oh, let me change it. Sorry, the view. Pardon me. If we're being asked that, which is what we are being asked, then what we do is we take derivatives of the function. Specifically, we take 2 derivatives to see if, once we take derivatives, do we get the sort of thing that the differential equation is saying that we should get? And that sort of thing that we want to get, we're really always trying to find out here is this whatever function we're trying, if we take 2 derivatives of it, do we get back itself times a constant times a negative sign? But that's like really what we're always asking here. We take some function, we're looking for functions, which if we take the rate of change with respect to time of that function, do we actually get back to that function itself times a negative times a constant? Because if we do, that's the kind of feedback phenomenon that defines harmonic oscillation, right? So the test, so what I'm going to do here is, and I know, okay, what I'm going to do here is look at my x function, and I'm going to take two derivatives and see, I'm going to take two derivatives of this and see if I get specifically exactly that, okay? So I'm going to just take two derivatives. I'm going to include chain rule. And again, I do this in the solution, but you're going to see there's a mistake in the solution. So I'm trying to be careful. So here I'm going to take, and that's also why I'm not asking you guys to do this now, because I'm just trying to be clear because it's exam, yada, yada. So again, the function that I'm dealing with, the conjectured, tested, that the function that I'm testing here is this. And again, like why? Just because I'm being asked. This is like a math question. I don't know what's going on with K and Q and R. I just know their numbers, but I'm just being asked a math question. I don't know why the math teacher made up the K. I mean, like why the physics teacher threw in the K and the Q and but it doesn't matter because I'm just doing math with them. It's like choosing the number 7 rather than number 5 in a random example. So I have that. So I take one derivative. I go like this. To take one derivative, first of all, I know that the derivative of cosine is sine. Okay. Oh, sorry. So there's going to be like a negative sign thing going on. But then chain rule, I have to multiply everything by the derivative of what's inside the brackets, right? And what's the derivative of that whole thing, I have to do the derivative. Because of chain rule, I've got to do the derivative of this whole thing, the derivative with respect to t. The derivative of this whole thing with respect to t. Well, the derivative of that is literally kq over r cubed, right? Like, or technically it's kq over r cubed plus 0, right? Because it's the derivative of this with respect to t plus the derivative of this with respect to t. But the derivative of this constant is 0, right? So, I mean, and I know we've seen this, but I'm just trying to, okay, so I get, so by chain rule, the like kq over r cubed comes out, like I do have to deal with that. But then I still have, so this is me taking one derivative with respect to time of that cosine function. Now I'm going to do it again. Why am I even doing it again? Because I'm ultimately interested in what the second derivative equals. Like that's what so I'm going to take this, and this is what we always do. I'm going to take the second derivative now. So the kq, so now chain rule again. Well, the derivative of sine is cosine. So the sine's going to change to a cosine. The negative sign is not going to be affected because the derivative of sine is cosine, not negative cosine. But then by chain rule, the constant's going to come out again from the brackets. Like I'm going to have to multiply everything by that derivative again. So I am going to get out here. Oops, sorry. Right. And again, I know we've seen this like once before in the homework number 2 in math methods, but just notice like that pi over, oh, not pi over 12, that pi over 2 is there just because it was there in the given, because the question is asking me to consider that function. Like, and we've seen before that it's not unreasonable for there to be a phase constant. So there is, oh, and I'm totally going to get, okay, let me just say this and then yes. But so the pi over 2 is there as part of the function. But when I do chain rule to it, it doesn't come out, but it does stay in. Like, well, maybe, so there's a question. I want to answer the question. I don't know if the question's about this or not, but like everybody, if you're confused at all about that pi over 2, you're all allowed to ask questions about it. It is actually part of what we're trying to practice right now is how to deal with that pi over 2. So, but Ardell has a question, but then anybody, but feel free to ask about anything. But yes, I'm sorry, Ardell. Go.
Why is the x not gone? Isn't it a constant?
Oh, no, because I'm an idiot. I'm sorry. Great question. I'm totally just that. I'm so glad. No good reason, because I'm an idiot. Hold on, let me put it back in. Thank you. Wow. This is my good question. And that counts as like 75,000 100 points. in the thing. Definitely put that in the game thing, please. I actually should open a portal. Oh, you know, I think I did one semester. I am going to open a portal for people. And I mean this, anybody who's gently in any way finds a way to gently point out that I might have made a mistake. That takes, I mean, I know for some people it's like, you know, the greatest moment of their lives when they prove that somebody else is wrong. But for some of us, it does take a little guts to no, just Ardell is absolutely right that I totally just dropped the X naught for no good reason. Absolutely right. Thank you. Wow. Okay. And that really should be submitted for points. Really, really. Hold on. So we have this. Yeah, for like 1 year of my teaching life, like maybe when I was like 22, I occasionally thought you were supposed to, as a teacher, like do intentional errors to see if people were paying attention. That I tried that for like 1 year until I realized, like, oh my God, yeah, that system works if we know for a fact we're never going to accidentally make errors. But if you're going to actually make errors, you don't. But yes, okay, all right. So thank you. No, that's a good correction. So then, if that's true, do people accept where we have so far? I'm saying we've got this so far. No, that's awesome. And it's really important, by the way, that Ardell said that. Okay, it's not even just like an error that I dropped the X naught, but it sure is important. She's right, because the once you've taken the second derivative, the thing that all of us have to do, and this is the step that I always forgot in college, honestly, the step I'm about to do now is the part that always eluded me if someone didn't tell me to do it. Like I would look at this on an exam, the thing we just wrote, I'd be like, okay, I took two derivatives. I know I'm supposed to be figuring out whether like this matches the original or something. I'd look back at the original. I would look at like this thing and I'd be like, all right, that's a nice, tidy, like short equation that intimidates me, but it's like short. And then I'd look at the thing that I have and I'd be like, I have no idea. Like, what does this have to do with that? I have no idea what I'm supposed to do, because I would always forget that the thing I'm supposed to do, and this may well be why Ardell noticed like that the X naught was missing. The thing I'm supposed to do at this stage now is go, oh yeah, all of this business right here, that's the thing that I'm trying out as X. Like that's what this says, right? Like we're trying it out. That's what's tricky about this. I don't know for a fact that X does equal that, but I'm testing the hypothesis that like this is a mathematical experiment. I'm testing the hypothesis that that X equals that. I'm seeing what, and the way I'm testing it is if it did equal that, do I get what I want for Christmas? And the answer is no, because I'm Jewish. But no, but yes, I do. So I go over here and I'm like, oh yes, this whole thing here is what I'm testing as X. So it doesn't prove right or right. Doesn't mean I'm done, but it just means, oh wait, okay, I can now start making sense of this. Apparently, what I've just concluded is that the second derivative of X with respect to time equals negative times some kind of constant, some kind of complicated, maybe even squared constant, but nonetheless a constant, all times something that I'm calling X. So now this is, now here's where the error, or here, so far everything I've done here, I think in principle is what I did in the solutions. But now I look at this, and I have to be very careful now to all of you. I'm not, and notice, I'm not even going to ask you like what you think your answers are. I just want to try to say clearly, if I look at this right now, if I look at this, okay, the actual answer to the question as stated, does this satisfy the original differential equation? Well, the answer is no, which I did not put in the solution. The answer is no, because the differential equation that was presented, the one that was given in it, is right here. There's no squared there. There's no squared there, right? Like the problem says, given this, does this, in other words, there's no, in other words, well, let me just say it again clearly. The answer to A sub 1 of part 1 of the whole exam, the answer is no. This cosine solution, although it looks very good and it's very well constructed, it's very intelligently designed, and even though it has things in it that maybe we don't know or are complicated, it's all very like nicely designed and almost looks like it would work, but it's off by a square root, if you want to put it that way. Like this cosine does not satisfy, excuse me, someone's going, this cosine function as given does not satisfy the differential equation as given, because the differential equation as given was this, sorry, which I just erased. The differential equation that was given is this thing that I'm circling, right? But what we just found when we tried our cosine function that was given to us, we found that it made this differential equation, like this 2 right here. I'm trying to say to everybody as clearly as I can, this 2 right here, or put one other way, I'm saying, okay, to be as clear as I can as possible, like we don't know what K and Q and R cubed are supposed to mean. The truth is they do mean something in physics. That's why there's this problem. Like nothing is just being constructed just to mess with your head and just to be random. K, Q, and R cubed are actual real things in physics that you're going to see. This is like it's real, but it's what we're also trying to get you to see in physics is like the way to see things in physics is to come to see them. We don't see everything all at once. So I'm saying you don't have to know what K is. You don't have to know what Q is or what R cubed is to analyze this problem. You just have to believe that they are numbers, positive numbers. And if they are numbers at all, unless they are so trivial, like unless they're all 1, right? Or they're all very specially designed so that all together they multiply and make 1, which would be very, very specific and weird. If they're all just random numbers, then all those numbers taken together squared is not the same thing as those numbers. Like if all the numbers together make 2, then 2 squared is 4. 4 doesn't equal 2, right? So they are all just some constant that I don't know what it is, but whatever it is, it's not the same thing as itself squared. So when the problem is asking me, does the cosine function as given produce this differential equation where this is some constant that I don't know? The answer is no, it doesn't. It produced this other differential equation, one that's very similar, but had a different constant in here. Do you follow? Okay, so the answer is no. So that's the first thing I want to say clearly. The answer to to problem 1, part A, sub 1, the answer is no. The reason I'm trying to say that as clearly as possible today is that in the solutions that I sent you, in the very first solution, I wrote yes, even though I was doing the exact same logic as I just did here. I did the same logic, but if you look closely, you'll see that I made a mistake and just somewhere in there, I just invented the idea. Well, here, let me write this as clearly as I can. I just decided that the proposed X cosine function that they gave us to work with in the test, I just like stuck a square root in there accidentally to make it work because I jumped the gun and I was like doing exactly what like a student might do, a responsible but anxious student. Like I was so like wanting the thing to work that I accidentally miscopied the function and made it work. I put in a square, in other words, I put in a typo. In my solutions, I put in a square root in the cosine thing that's like not there in the actual exam. And that's my bad. That's just me making something up. So therefore I proved yes, because it's like, that's called like confirmation bias or something inside. And and if you did that on the test, by the way, I would be very reasonable about it. I would get what I would still couldn't give you full credit, just like you can't give me full credit. But I would get what anyway. So I will replace the solutions. I'm going to repost updated solutions, but I'm going to see all these errors before I do. So I'm trying to tell everybody in the room right now, if you're looking at the solutions I posted in the very first question, I did put a square root in there that doesn't belong. And I'm saying this is the correct answer. The correct answer is no. So I want that to, can you just like check out and make sure, and this is the way to do it. And it's the way I do the next 2 problems as well. But is everybody, so I'm just gonna let that sit for a second. Hold on, just see if everybody's cool.
Yeah, that makes sense.
Oh, thank you. Oh, thank you. I wasn't even, thank you. Both of you. All right. That's good enough for me. See, thank you, Isabella. Thank you, Ardell. All right. So all right, cool. Oh, and thank you, Ingrid. Okay, cool. I appreciate it. I know I'm so, I'm really, I won't say it. No, but thank you. And again, I will, when I post an update to this, when I post updated solutions, or when I distribute the full solution to the problem 3, which I haven't yet, anytime I do that, I'm just going to repost the whole document. Just again, like if I post solutions, I'm not going to just post page 3 or something. I'll post the whole thing. So all of you, again, whenever I post a new one, just throw out the old one. Just, assume that the new one supersedes, if that makes sense. But okay. All right, that's number 1. I will go one step further, I think, especially because you haven't had that many. Yeah, I'm going to go one step further, unless there's objections. I'm going to do part B. Wait, was there a part? Did I skip? Hold on. I do want to get to part B comfortably, just so that we all sort of have the same idea of how to do this exam. But pardon me for a second. What is it? I think there's a lowercase Roman numeral sub part 2 of this that I don't want to skip if I don't need to. Oh yeah. Oh no, I did. Okay, so right. So the answer is no, and literally, I would say this: when it says why or why not in Roman numeral 1, lowercase letter a, subpart 1. I mean, when it then says how, why, how, or why, how not, the why not is this line right here, that KQ over R cubed does not equal KQ over R cubed squared. Like, that's why not. Like, that's the reason. Okay, everybody, if that's cool. So now I'm going to go on. I'm just going to keep going in order so I don't confuse people more. I'm going to quickly do now a lowercase Roman numeral 2. I'm going to quickly do it, but I'm going to say in advance, yay, go Rama. I'm going to quickly do it, but I'm going to say, if you're following this, so that was, sorry, this was, okay. So now what we're going to do is, okay. Oh yeah, okay. Okay. So the next question, notice we're still assuming the same original differential equation. Like, that's why this is all a part of part A, right? In part A, we're given this differential equation, which I want to say, hopefully we recognize is some kind of harmonic oscillator, right? Like, I mean, it's not saying that, but hopefully we see that the reason for this math is that differential equation is some kind of harmonic oscillator, but it has something to do with K's and Q's and these numbers that we don't know anything about. And that's the purpose. Like, that's why it's an exam problem, or that's why it's the new frontier. But we're seeing, okay, this is some kind of harmonic oscillator. And first we were asked to test if a certain cosine solution would adequately describe this oscillator. Could we use that particular cosine solution to describe where the oscillator is at any time? And the answer is no. We found out no. Now we're trying like a complex exponential solution. I think these expressions are starting to look intimidating. I'm not trying to make them more intimidating by saying that, But I want to acknowledge, like, even when I look at these things, they look thick and messy to me. And I definitely still remember what it was like when when I was learning them, they look very scary. Like, I can't believe I'm being asked to do math with things that are that thick. Like, there's about 5 letters just in the exponent alone of E. And then one of those letters says I. Like, it's crazy town. But part of the thing that we are trying to do here, part of the thing that we're trying to get across is that a lot of math is this process of what people call, I think, lumping. Like, you really want to take all the letters inside that parentheses of that exponent and lump them together and just treat them as one letter. Like, that is part of what we're trying to do. But anyway, so we're going to do the same thing here. I'm going to differentiate that expression twice, see if things work out. This time, I'm actually talking way too much, because this time I'm going to do it again, just like in part 1 and just like I do in the solutions. I want to say, though, it's worth doing them because here too, what am I trying to say? Here too, for the exact same reason, we're going to find that the answer is no, it does not satisfy, because we're going to be off, like, in effect, by a square root factor. Like, it's not going to work, because truthfully, if we wanted this to work, if I wanted it to work, I should have put a square root in the exponent of the E. Now, I didn't. But if you're seeing what's happening, we're going to see it's not going to work again. But that's still a valid answer. The answer is going to be no, it's not a solution. So here we go. Anyway, but again, I think I said that wrong in the solution, so that's why I'm doing it. So 2. Okay, so so this is, again, chain rule and the rule that e to the blah, the derivative of it will always be e to the blah. So we have right, that's one derivative, right? In other words, what I just did the same thing I did in the first part of the problem, with the cosines, but I really did do the same thing, chain rule. But notice I'm treating I like it's just a constant. Like, it says in the test, assume that I triple equal sign equals square root of -1. Yes, that's true, and you should assume that. But and that's all you have to understand about I to do all of this stuff, which is sort of cool. Like, all you need to know about I is it's the number that is the square. It's what we mean by the square root of -1. But better than that, for our purposes, what you really need to know about I is that it doesn't change. Whatever it is just a number that is constant. So we treat it as a constant number, like when we do these derivatives and everything. So the I came out, excuse me, the I came out of the exponent just like the K and the Q and the R cubed. Okay, so we have that. Now we do it again, second derivative. So now I got to be really careful. And I must have botched this like 4 times in the solutions, actually. Again, I'm going to do chain rule, right? So again, I have to be really careful. Oh, yeah. So everything comes out from chain rule, all those exponents, including the I. So I get, I get magnified for no reason. I get I squared and all this garbage squared. I mean, maybe that's a weird way to write it. But the x naught is not squared, right? Ardell's x naught is not squared because it's just been sitting there. It wasn't in the exponent. So we have that. That's the second derivative, right? And then before I go any further, I look, well, first thing I do is just like before, I go like, oh yeah, all that business. And maybe x naught is always the signal to remind me to do that. I don't know. That might be a good point. But all that is x, so that's something. But then also I notice I better remember that by definition is -1, right? So what do we have so far? We got hello. We have Okay, so we get this. So I guess I should have asked, but to cut, oh, I'm sorry, hold on. Sorry. So I say right here that technically, so the answer is no. Again, oh wait, chat. Well, I'm going to say it, and then I'm looking at that. I say the answer is no for the same reason as before, that we wanted, and you know, in a way, this is a technicality, but this is all technical. I mean, this is math, right? I mean, these are details that do govern. So we wanted this to be true. But what we got was something that looked similar, but you know, was different. We got a different constant. So the answer is no, it does not satisfy that differential equation. That's the answer to that, but let me look in the chat and oh, sorry. Oh wait, oh good. Wait, okay. Oh wait, so am I, sorry, am I, thank you, Ardell, for, I'm not sure if that's now, if, yeah, okay. So that was part 2, right? I think that was that. And again, the reason I just, again, for anybody who's listening, the reason I just did both of those somewhat loquaciously is because I believe that in both of those, there's a subtle error in my solution. So you should please, like, and again, I will repost, but like, you know, if you might want to sub these in, or, you know, these take priority of whatever I put in there. The method and everything is the same, but I did miscopy something in there. So the answer we get so far is no, no. Now I'm going to go one step farther with this. Wait, 350, this ends. Yeah. What I'm going to go to one more to show you now how this cleans up its act. Like basically the subtle difference between A and B. And then I think hopefully that, you know, hopefully C will be clear to you just from my solutions then. But what I want to say about B now then. Well, although again, please stop me. If anything I just said was unclear about any of that, I mean, and again, you're allowed to admit to confusions in calculus. And even if you want to put them in direct message, I promise all of you, this is our secret opportunity to get calculus in some way that actually helps in science. This is, again, even if I can't even if you just want to put in direct message to me, like this calculus thing is still freaking me out, even if you know that I know that we can't talk about it right now, you're allowed to tell me that. Just saying, okay? Partly we're at, yeah, because this is where the calculus is happening. I mean, but okay. So you're allowed to stop me, but other than that, I'm going to question B. I think it's B, yeah. So now we're still in 1, which is the math, but now we're in part B. So now a slightly subtle thing happens. We're now in part B because all of what made part A was that it gave us a differential equation and it asked us to test different solutions to that equation. Now in part B, it does not give us a differential equation anymore. This is a slight shift from math to physics now. Now in part B, I mean, it does give us equations, I know that, but it doesn't give us a differential equation in part B, right? In part B, it just hops right in there with this cosine thing, which may or may not be intimidating. Yeah, part B, it just hops in there and says, basically says, consider, hello. It says, consider, I'm saying, consider this. Okay, it just consider this. Now, this is a cosine function. Obviously, we've got cosine functions in our class, but it looks it's not exactly any function we've seen before, right? I mean, it's got an I, but the I is in a funny place. We still got these crazy K and Q that we don't know anything about. Again, this is intentional, right? Like what makes this an exam or whatever is that we're really trying to see, do we get these concepts even when they're dressed up in slightly unfamiliar forms? Because really, that's really what we use math in physics for, is to be able to discover the universal in the particular and vice versa, if that makes any sense. So what I'm saying here is, okay, we're going to consider this cosine function. We're kind of, what we're saying now is like, all right, we're sort of seeing that cosines sometimes describe oscillators, and sometimes using I describes oscillators if we do it the right way. But what if we put them together this way? Can we describe an oscillator this way? And so the question, and this is a subtly different now question, does this position function describe an oscillator? Now I try to emphasize this in the solutions here too. Now, this is a slightly different. This is more of a physics question now. Now we're just saying, given that math description above, does that actually capture a true harmonic oscillator? Which means now, does that thing satisfy? If I differentiate that twice, will I get a differential equation that accurately is an oscillator equation? Meaning, well, what this is really trying to test in us. So this is a slightly different question now for me. I'm saying, like, if there's one big point about this whole topic, this whole chapter, if there's one way to summarize the whole thing, it's this. I'm going to keep writing this thing down here at the bottom with the z's. Okay, in my mind, actually, that this if differential equation, then cosine solution. This to me really is the essence of the entire chapter that, like, we're trying to beat down from every detailed level. The real heart of the matter is, if we ever see that differential equation describing some variable z, then the variable z is harmonically oscillating at a given and known calculable frequency. Like, that's our big story. But the way you'll know that you're really getting this and seeing how it's the same story in all these different questions is if you really get when and why I transitioned to using z. Like, the reason I'm using z is to emphasize it could be any variable. Like, you need to be able to recognize this pattern, even if the variable is theta, like as it is for the next problem in the exam, or even if the variable is x, or if it's e, like E field, which it will be for the next chapter of this class. Like, you have to understand that I want you to understand that whatever z is, as long as it fits that differential equation, then it will be solved by that cosine expression. And you need to understand that whatever's in the parentheses, it might not look like an omega, it might not look like a z, it might not look like an omega squared, but just whatever's in the parentheses, as long as it's a constant, then the square root of it is the angular frequency of the oscillator. So why am I saying all this right now? I'm saying then that anything that can be described by a differential equation of that form is an oscillator. And whatever the actual constant of that form is defines the particularities of the oscillator, the rate of it. So all I have to prove in this question, if I'm trying to answer, is this cosine function a harmonic oscillator or not? What I'm trying to say is, as long as I can prove by taking two derivatives that it looks like this thing, regardless of what omega is, as long as it looks like this thing, then it is an oscillator. And I think that is what we're going to find. I mean, to cut to the chase. Okay, what time is it? It's 3, 4. All right, so that's what I'm going to do. But in other words, in part A, I differentiated twice, and then I had to see whether my second derivative thing fit a specific exact differential equation that was given to me. Here, I don't have to fit a specific exact one. I have to fit the general form. I mean, you'll see but that is a distinction. So, all right, so I'm going to take two derivatives here again, just like before. I'm going to take two derivatives. Okay, so I'm going to take the first derivative. Same thing as before, chain rule, all that. But notice now the I, unlike with the exponent thing, the I here is not in the parentheses. The I here is not like a coefficient before the t. The I is a coefficient before the whole cosine expression. In other words, it's functioning like an amplitude, not an angular frequency. Just notice that. I mean, I don't have to but just be aware. So what? Well, so when I do the chain rule, I'll get this. And there's no x naught this time, by the way. There just isn't. Oh, I shouldn't say that, especially not to Ardell. Like here, you might notice there doesn't seem to be a term called x naught. That doesn't mean that my units are off or anything is wrong or anything. It just means that what x naught actually apparently is 1, right? Well, and then times I. But you see what but anyway, I mean, it's 1 times I. But all right, anyway. Sign, no, I'm mistake again, sorry. Hello. Oh yeah, they're not called lumps. They're called chunks. That's what you don't lump together the KQ, you chunk it together. That's the cognitive psychological term, I think, is chunk. It's a very technical term. But anyway, so that's one derivative. And now here's the other derivative. Now I gotta be super careful, maybe, or at least super aware when I do this second derivative now. Okay, chain rule again, that KQ over R cubed thing is gonna come out again, but it doesn't involve an I. Right? The I is not getting squared here. The KQ is. So I still just have this negative I times KQ over R cubed squared and now cosine. Right? So now I have this. Right? This is what we have so far. I'm just going to recopy that on the next page, but stop me if I'm wrong. I'm looking at the chat. I'm just going to recopy that on top of the next page and then do the next thing. So far. It's starting to look complicated, right? But but it isn't if you just look at it part by part. It's no more complicated than a long sentence of English, which can be very complicated. And I might be losing, but I believe this is what we have so far. We have this. So now I say, wait, it's correct. Well, yeah, that's what we have so far, right? So now I'm just going to, multiplication is commutative. So I'm just going to make one thing a little clearer to myself. I'll just go like this. Okay, so we have that. Now, why'd I do that? Again, I'm just going to keep calling it. So I did that. I made that little rearrangement just so that I could make myself aware of the fact that this whole thing with the I in it is called X, right? So we have, so that thing's so annoying. Okay, so we have this. Now, in the first problem, I would go back and compare this to the given differential equation and say, okay, is this the original differential equation? Like, if so, then the answer is yes. And if not, not. But here, they're just asking, is this thing a harmonic oscillator? Okay. Now, well, actually, I guess I'll ask you that. Yeah. So, well, should I ask? I don't know if I should ask you or not, but well, I'll just say, the answer is yes. This is a harmonic oscillator. Like, I know that the constant here is being squared, but I was never told what the constant had to be. Like, in other words, so, okay, what I really want to say is, oh, in fact, I know how to write. Yeah, like the question is this a harmonic oscillator? I say yes. It might not be the harmonic. I mean, it is, yes. But I could imagine why there might be confusion, because it might not be the harmonic oscillator that I might have expected. Like, I might not like the fact that that parentheses, that constant of proportionality in the parentheses is squared. In fact, I didn't like it in part A when it was squared. I said, oh yeah, see, that's a big enough difference to make a difference. Like, we didn't want that thing squared. But that's because in part A, they specifically told us what harmonic oscillator they were interested in. Here, we're just being asked, is it a harmonic oscillator at all? And I say yes. Now, how can I really prove that I'm right? Well, interestingly, in part A, it said, why or why not? And we said, why not? Because KQ over R cubed does not equal KQ over R cubed squared. That's why not for part A. For part B, if it's asking why or why not is this thing a harmonic oscillator? Well, it says in the next part, it says, if it is, give its period. That's a very reasonable question. Because if I'm saying something is a harmonic oscillator, in effect, what I'm saying is it oscillates at a steady rate. So, and period is the reciprocal of rate, right, of frequency. So in effect, what this question is saying is, if you're so sure that it's a harmonic oscillator, why don't you show us by showing us that it has a steady rate that it's oscillating at? If you could find that or flip it and call it the period, then you've really shown that it's an oscillator. So, okay, I'll do that here. Up by cracky. In the next page, I will solve for the period of this supposed oscillator, supposedly harmonic oscillator, to show that it is indeed harmonic. So I'm talking, and I know this will be one of the last things we do. I'm talking about that. I'm talking part one. Yeah, still part one. No, problem one, I mean. Problem one, part A, subpart, no, sorry, part B, subpart 2, right? That's what I'm talking about here. And it says, if not, why not? But if so, and I'm saying so, determine its period expressed in terms of given constants. So it's saying compute t. Well, here's how I do this. And this is given, again, given. We're computing t, assuming uh, I'm being asked to compute the period here. The way I know to compute a period, and the reason I believe that I am being asked to compute a period is a reciprocal of standard frequency, right? Like period is cycles per second, standard frequency is seconds per cycle, right? And where do I get standard frequency from? Well, standard frequency, cycles per second, is merely angular frequency divided by 2 pi, right? Because angular frequency is how many radians you cover every second. And the idea is that there's 2 pi radians in every cycle. By the way, happy Pi Day yesterday, which is also Einstein's birthday. So wow. Are we okay? Sorry, 1 second. Wait. I'm just gonna. The stuff that I'm writing in red at the bottom is correct, but I want to make it big. It's too important to be crammed in there, so I'm just going to start one new page and write it bigger. Bear with me, and I can turn back this page if you want, and then we're going to wrap. I mean, we'll be done with. We'll end on this note, but let me make this clear. just to be as clear as I can about this, and and then pretty much that, I think yeah, we have like 7 minutes, but just to be totally, now we're moving to the physics, right? Of course, the physics is inextricably tied up with the math, but in B, and C, by the way, C will be exactly the same thing as B. If you understand B, then C is practice, try C and you'll do it the exact same way. But what I'm saying here in B is if you differentiate that cosine expression twice, you get a differential equation that does have the form of simple harmonic oscillation, i.e. it's a second time derivative equals negative times some constant times variable. It is a harmonic oscillator. Its angular frequency is the square root of whatever is that constant of proportionality right here. So it's a harmonic oscillator. It has angular frequency KQ over R cubed. And if you want the period, then you divide the omega by 2 pi and you flip that and you've got the period. Just so you understand, like if it had, even if we had been, like even if the KQ over R cubed hadn't been squared, as you might prefer, or as it might seem more comfortable, that too would be a harmonic oscillator. It's just that that's an oscillator with a slower angular frequency, with an angular frequency of the square root of that constant. So like that's how it works. Like to be a harmonic oscillator, you got to fit that form, but then the specifics of that form tell you the specifics of your oscillating rate. I don't think we're going to, so let me just check. I don't think we're going to do much more. I mean, I'm not going to start a new one today, but I hopefully, again, that means that my solutions for the first couple are like messy and I don't want to write all over them. And like, I'm just going to, again, give you an updated solution set that's just correct with that. So for now, just look at, I hope you understand, like whatever you're doing in class today supersedes what handed out. So far as I know, the rest is correct. I don't want to talk through every single detail of the whole thing. I definitely will talk about, but if you're intimidated or worried at all about problem 3, believe me, that I'm fully going to walk through problem 3. Just if there's any concern about that, I'm not waiting for questions on problem 3. When I do problem 3, which Wednesday, I will fully walk it through. So you should certainly leave that for last, but 1 and 2 are, I'll give you one other hint for number 2. Sorry, I'm just saying so much and then I'll just pause and see if there's questions. But for part 2 of the whole exam, like after you turn the page and you see this pendulum, obviously there we're starting to get more physicsy. Now we're trying to relate this harmonic oscillation stuff to what you did in the lab. It's still all the same equations, still the same math, but we're trying to relate it to lab now. One hint for that, like what's the intimidating piece of that problem, is that right away it tells you that this pendulum that you're looking at is way deep underground. That's a weird thing to say. Like, why are we saying that? We're saying that to tell you something, to tell you that you should no longer assume, you should not assume that the value of G, of lowercase g, of the gravitational constant free fall acceleration, that don't assume it's 9.8 for the problem. You don't have to know what it is and you don't have to use it at all. But we're actually trying to caution you. There's shortcuts that you might get from the web where you think that would help with the problem, but they won't, is what we're like. In other words, even if you know that T equals 2 pi square root of L over G, which is fine, and don't use that in part 1 of the problem to get, just trust your knowledge of differential equations in part. So I'm being very vague. In the pendulum problem, one of the first questions it asks you is what's the angular frequency of this pendulum? Like if you're looking at it right now, I think it actually is first it asks for a free body diagram, and then it asks like calculate omega, angular frequency, to 3 significant digits. Okay, again, I'm jumping around. This is part 2 of the midterm practice exam, and it's of part 2 on the pendulum. It's called hook on a hook or something. The second question asks you to get angular frequency. What I'm trying to say right now is get that by looking at the differential equation, just like we did here. Like understand that the angular frequency is the square root of the constant of proportionality in the differential equation. Like that's the way you want to do that problem. It's not meant to be a trick or hard. That's what we're asking you to practice. If you were to try to get the angular frequency by doing some funky thing with 9.8, it would be a mistake because we're actually not assuming 9.8 at the beginning of this problem. That's what I'm trying to say. Okay, that's like a lot. Okay, so sorry to, this is a bit of a vomit session, I guess. But I'm not going to try to say, we've got like 2 minutes. So let's just sit. If there's any questions at all, I'd like to take them. Oh, but then I do have another class right after this. So if you're good, whoever you, all of you are, if you're good, if you think you get this, you're okay, then please say goodbye. And then we're both good. If not, I'll hang for a second or two.
Bye. Thank
Bye.
you. Have a good one.
You too. See you. Thank you. See you.
Thank
Bye.
you.
Have
See
a
you
good day,
Wednesday.
Professor.
Yeah, see you Wednesday. Awesome. Thank you. Bye.
Thank you, Professor.
Thank you. Awesome. Thank you. Goodbye. Thank you. Awesome. Thank you. Goodbye. Thank you. Awesome. Thank you. Thank you. Awesome. Thank you.